So Masahito's title is Quiver, Yangians and Crystal Melting, I see. Okay, please.
Okay, thank you so much. I hope everybody can hear me.
Yes.
Yes.
Okay, thank you. So if you don't hear me, please let me know. So and also, it turns out that there is an internet, let's see, kind of a maintenance coming in an hour, which shouldn't affect my talk. But if something happens, I need to reconnect. But I don't think it's going to happen. But let's see. Let me first thank the organizers for organizing this workshop for this difficult time. And it's unfortunate that I cannot make it. But I hope that I will get back to normal soon. And so this talk is about Quiver Yangians and crystal melting. And this is a working collaboration with Wei Li and also Dima Garakov. And so the first paper is in March last year. And so this is a paper we introduced algebra, and then we derived the algebra from more physics arguments in the second paper. And now we have yet another paper on the same topic where we generalize the representations. And certainly there are a lot of talks. Let's see, there are a lot of related works in the literature, which I'm going to mention. And also many of the technical ingredients is based on my earlier paper with Hiroshi Oguri when I was a student and summarized in my thesis. So let me begin with some overview. So this is a session of integrable models. And what's nice about integrable models is that integrable model sits at the intersection of various different things. In particular, algebra, which I mean by Yangians and things like that. And of course, the representation theory of that. But it's also the case that we have other ingredients. For example, sometimes combinatorial structure appears. There is underlying geometry. And so that's the story of geometric representation theory, etc. So these are all related with integrable models in one way or another. And it's also the case that there are a lot of physics inputs. Sometimes combinatorics comes from statistical mechanical model, or they come from gauge series and string series. So this is a recurring theme in integrable models. And my talk today can be regarded as an example of this phenomenon. And in my talk, I'm going to talk about a new algebra, which you can regard as a building block for a new integrable structure, in the sense that it's a generalization of the Yangian. And we call it a shifted Quiver Yangian. Shifted just means some generalization, which I'm coming to later. So what is a Quiver Yangian? So as the name suggests, it's associated with Q, the quiver. And so hence the notation. And it also depends on extra data, W, which is a potential, which I'm going to introduce later. And this Quiver Yangian is a generalization of affine Yangian. So Yangian associated with the affine real algebra. And so as the name suggests, it's associated with the quiver and the superpotential. So if you're a physicist, you can think of it as a defining data for some supersymmetric quantum mechanics. So this is a new set of algebras. And we also have representations for them, which is actually highly non-trivial representations. So, and the representation is constructed by starting with some statistical mechanical model of crystal melting. Here it's found by this lambda, where lambda denotes the crystal. And so we have some representation space leveled by elements of the crystal. And the shifted Quiver Yangian acts on this crystal melting, so it gives us a representation. So in that sense, there is a nice new algebra, kind of integral model structure. And then there is a representation acting on combinatorial structure. And again, this crystal melting can be derived starting with supersymmetric quantum mechanics. Well, finally, if you're interested in the geometrical aspect, it's also the case that there is underlying geometry. And the underlying geometry, in this case, is the toric-Calabi-Yau threefold. So combinatorially, it's associated with some convex polytope, lattice polytope in 2 dimensions. And there are a lot of interesting enumerative invariants people have discussed. For example, Donaldson-Thomas invariance, or also known as the BPS state counting in physics terms, and the wall crossing, etc., has been discussed. And these are represented by crystal melting. And it turns out that the partition function for this BPS state counting, Donaldson-Thomas counting problems, can be regarded as a character of this shifted Quiver Yangian. And eventually, everything comes from string theory, although I'm not focusing too much on string theory aspect today. So let me start with the definition of the Quiver Yangian introduced in these papers. So in order to define this algebra, we need to start with the quiver and the superpotential. And quiver and superpotential is, in my talks, are associated with the toric characteristics, although the definition itself works more generally. So, okay, so what is the example for the quiver? The simplest example is this one, the first line. The quiver is a one-node quiver with 3 arrows, which I denoted x, y, z. And the potential, superpotential, is trace x, y, z minus x, z, y. And the meaning of this is that if you differentiate this with respect to x, y, z, etc., for example, if you differentiate with respect to x, you get the equation like y, z equal to z, y. So z and y commute. So it turns out that all these three commute if you impose that Jacobian with respect to this potential, and that represents the C3, the flat Calabi-Yau geometry. And similarly, you can have another example. This is the second line. You have 2 nodes and then 2 arrows in between, and you have some potential. And it is known that it corresponds to conifold. So if you're a mathematician, you might know from this some work of Vandenberg about non-commutative Krepan resolution. This is also discussed in physics in the ADS-CFT correspondence by Krepan-Witten, for example. But in any case, it corresponds to conifold geometry. So and furthermore, there is one more example. This is a 4-node quiver with 8 arrows in between with some complex superpotential. And it turns out that this geometry represents the canonical bundle of a P1 times P1, which is also toric Calabi-Yau threefold. So there is an algorithm for writing down these pairs of quiver and potential. And once you have this pair of quiver and potential, there is associated moduli space which reduce the original toric Calabi-Yau. For this purpose, for the purpose of my talk, you can regard Q and W as an input. Now, there is once given this Q and W, you can assign extra parameters, which I call the equivariant parameters, and denoted by H. So the equivariant parameters are associated with the edges of the quiver, which I denoted I, so hence the notation HI. So for example, in the first line, there is for associated C3 example, there are 3 arrows. So there are 3 parameters, H1, H2, H3 for each of the X, Y, Z. And then it should be consistent with the superpotential, meaning that the sum of this equivariant weights should sum up to 0. So in this case, the sum of H is equal to 0. So there are 3 parameters with 1 constraint. And similarly, in the second example, we have 4 arrows, so 4 parameters, but then there is a constraint that superpotential have net weight 0. So there, in this case, it gives us 1 constraint, leaving 3 parameters unspecified. So these are the parameters I call the equivariant weights. So hopefully, so far it's very clear. So Q and W, and then equivariant parameters are associated with them. Now, what are the generators? So I'm going to define the algebra, so I need the generators and relations. So what are the generators? So the generators are given here. So it's like a Shubari type generators. And there is an index A, where A is the quiver vertex. So for each vertex of the quiver, there is a set of Shubari generators, E, F, and psi, where psi is a Cartan part. And each of these generators are functions of the spectral parameter, formal function of the spectral parameter, which I denoted Z. So it's just like a Yangians. But then so you can expand with this spectral parameter to obtain infinitely many modes, E and A, F and A, etc. And for E and F, the sum runs from 0 to infinity, but for psi, it runs from minus infinity to infinity. So it's kind of double. Sometimes people call it a Cartan double. And you can try to truncate it to finite expression. So you can say that this starts on some finite number, minus k, for example. And in this case, you can say that it's a k-shifted quiver Yangian. So there is a shift you can introduce if you like. So k-shifted Yangian is contained in the most general case with n equals to minus infinity. So in any case, these are the generators. And the final ingredient is Z2 grading. So this can be going to be something like a super real algebra, but it's not a real algebra, but there is a Z2 grading. And the Z2 grading is determined to be 0 or 1, depending on whether there is an arrow starting and ending at the same vertex. So this is represented by the bottom. So for example, in this case, there are 3 arrows. There is at least 1 arrow. In these 2 cases, there is 1 arrow coming back and forth, coming back to the same vertex. So these are even. So grading 0. But there are other vertices where there is no such arrow. In this case, you declare that it has grading 1. So it's like a fermion. Now, you can define the relations in the algebra. So okay, so this is the final relation. So here you define the generators, and you have the relations. So size and f's. So we have all sorts of combinations. Here there's a bracket. So this is a super commutator. So it's a commutator when both are it's an anti-commutator when both are odd. Otherwise, it's a commutator. And z and w are spectral parameters, and delta, I forgot to say, is z minus w. So it's a difference between two spectral parameters. And then there are some factors. Okay, so for example, for psi says that the psi is mutually commute, but psi in these there is a function b bar phi. What is this bar phi? It's defined here, and I called it the bonding factor. And bonding factor is some rational function, and so it's a product of all the edges from A to B. And then for each of these rational numerator and denominator, it either has a poles or 0. And the pole is determined by the equivalent weight of that edge. So recall that I introduced the equivalent weight. So these are the parameters associated with the edges. And so these are and they specify for each arrow from A to B, there is associated B to A, there is associated 0, and A to B, there is associated 4. So this represents the definition of this function. So up to this function, they commute. Sometimes there is a Z2 grading, so you have to be careful with the plus minus sign. So I hope I explained everything, except that there is an equality. So equality here means that, okay, so these identities you're supposed to interpret by expanding Z and W. So recall that each of these generators, you can expand with spectral parameters. And when you expand, you have to be careful up to which terms you impose the condition. And so depending on these different types of equality, you get slightly more stronger condition, for example, here in this case. But in any case, so you can expand this very complicated these things and obtain very complicated commutation relations. So, but it's easier to remember this way. So this is the definition of the algebra, which seems to be a new algebraic structure we introduced in our paper. Now, what is the special cases? So what are the special cases? So the special case associated with C3 geometry. So that's the case, as I introduced before, this particular quiver with particular potential. And it turns out that in this case, if you work out this particular case, it corresponds to affine Yangian of GL1, GL1 hat, Yangian of GL1 hat, which is discussed in many people. Well, in fact, Miki, Ding, Hara, etc., they discussed the quantum toroidal version, and later people defined affinization, etc. Perhaps I should mention Fagin et al., for example. Fagin, symbolic, Prochaska. Many people have certainly talked about that, and this algebra itself, people also discussed in connection with AGT, Moriko, Kunkov, Schiffman, Barcelo, etc. So there are a lot of discussions of this algebra. Now, for the quantifold case, this another example which described earlier. In this case, it turns out that it gives rise to affine Yangian of GL1/1. So it's a Lie superalgebra. And similarly, you can start with more general quiver, more general toric parameter threefold, which is described by this equation: x5 equals z to n, w to m. So you have 4 complex parameters with 1 complex equation. So we're leaving 3 complex parameters. So it's a threefold, and it's Calabi-Yau. And in the toric diagram, it's like this. But anyway, it's this equation. And then associated, if you define, work out the algebra, it's the Lie superalgebra. But the point is that if you discuss general toric Calabi-Yau 3, you get some algebra, which is defined in the previous pages. But in these cases, there is nothing like finite dimensional simple Lie algebra associated with, or even a fine version. And so it's very interesting, in my opinion, to try to study the representation theory properties of this algebra, new algebra, and what type of algebra it is. Now, for me, of course, I just defined it. But the motivation for this comes from twofold. First of all, I can construct a well-defined representations of this algebra, which ensures the consistency of this algebra. And second, you can derive it actually starting from some underlying Quiver quantum mechanics and gauge theories. So let me first discuss the representation theory part. And the representation uses the crystal melting. And the word crystal melting appears is probably best known in the case of the plane partition, 3D partition. So it's something like this, and it's taken, you take a set of boxes from the corner. And hopefully the definition is obvious from this picture. And the way to see that is that, okay, for the C3 case, this is the quiver for C3. So there are 3 arrows. And there's a nice correspondence between this quiver and this picture of the plane partition, in that you can start with some vertex. In this case, there's just one vertex. You take that vertex. And you draw X and Y, Z, etc. Along some directions. And each of these equivalent weights have X, Y, Z, 3 arrows has equivalent weights. So you can actually draw this set of arrows depending on the equivalent weight. So equivalent weights is like a 2-dimensional coordinate system. So there are 3 parameters with 1 constraint. So there was 2-dimensional parameter space. So you can draw these arrows on the 2-dimensional plane. And so you can start with some particular vertex and draw a set of paths. And sometimes you end up in the same place because, for example, X, Y, and YX, if you go around the square in a different ways, you arrive at the same point. But that's represented by this relations arising from this Jacobian of the potential, which says that in this case that X, Y, and YX commute, for example. So the lesson is that if you start with some particular vertex and consider all the possible paths, modulo the relations coming from superpotential, and then you draw some 2-dimensional picture, and if you uplift it naturally, you get some 3-dimensional picture, and from here you can start growing the crystal. And it turns out that this story generalizes to an arbitrary toric curve with 3-fold. And this is what I did with Hiroshi Oguri some time ago. And in the end, the story is exactly the same, although the pictures themselves are complicated. And so, so this is another example. So this is the example associated with affine Yangian GL2/1. But the point is that whatever the toric curve is 3-fold, there is associated quiver and relations you can write down. And starting with this, you can assign your equivalent weights, etc. And you can choose a particular vertex and draw a set of all possible paths from the vertex, again, modulo the Jacobian relations. And for each path, it has a definite equivalent weight, so it defines the points on the 2-dimensional plane. And if you uplift it, you can define a crystal like this. So this is, it looks intimidating, but it follows exactly the same type of logic and define the crystal. And the geometrical underpinning of these is that these actually arise from some fixed point of the torus fixed points of the moduli space. And that's why these are relevant for Donaldson-Thomas invariants. For now, for this purpose, this gives a set of states relevant for representation of the Quiver Yangian. And so this itself is a vacuum crystal where nothing is taken, but you can start taking the crystal. For example, there is a top atom here, you can take one. And then the next step is to take another atom whichever one is connected. In this case, there are 3 different choices. So you keep taking the atoms from top, and then that defines the molten crystal configurations, which is a generalization of the 3D partition. And from given this such a crystal melting representation, and then crystal melting, you can construct a representation of the Quiver Yangian, which I introduced earlier. And so this formula looks a little bit complicated, but the structure is simple. So first of all, what is K is the configuration of the molten crystal. So I call it a crystal. So a finite set of atoms taken from that vacuum crystal, which I showed earlier. So, and then there is a Shubari generator, psi just acting on the state with some particular factor. But E and F are Shubari generators. So as you might expect, it increases the atom by 1. So whenever A, there is a color. So whenever you can, so here, I forgot to say that there are 3 different colors because in this case, there are 3 different vertices. And it's a similar story in general cases. So there are as many a number of colors as the number of vertices of the quiver. So if you start with a path and then from a vertex, it ends on some vertex. If you go around on this quiver, it ends on some other vertex. So if you, so depending on what the endpoint vertex is, you can associate different colors, which is shown here. So, for this Shubari generators, there is associated Shubari generator, EA. For each vertex, there is associated raising operator. And whenever you can add an atom to the crystal of that color, it contributes non-trivial to the sum. so it increases the atom. So that's what shown by here, k plus a, where plus means to add the atom. And similarly for the F generator, which removes the atom. Now, another crucial part is that it's spectral parameter dependence. So here, if you look at it, there is a pole at that location. So whenever you can add, for example, or remove atom, there is a corresponding pole in the spectral parameter. And somewhat correlated with that, there are concrete expressions for this numerical factors, which I haven't talked about yet. So this psi is eigenvalue of the Cartan generator, and it's a product of this bar phi, which introduced earlier. So this is the bonding factor which appeared in the representation, in the definition of the algebra itself. And there is some piece which I'm coming to in the next slide. And the point is that there are extra poles for each atoms you can add or remove. There's a pole, and then you can take the residue with respect of this function psi and take a square root, etc. So that's this factor E and F, which appears in the definition of this algebra. And so, okay, so in the definition of the representation, and so this is a concrete formula, and you can use this formula and just check the commutation relations and see, prove directly that it is a well-defined representation of the Quiver Yangian. Now, so this gives, well, let's see, one representation. So if you take the psi 0 to be some particular form, which is like a 1 over z. So, okay, so there's this psi 0, which is shown here, which is extra ingredient, which I haven't shown. And so suppose that this thing has a 1 over z, the spectral parameter dependence. And that means that it has a pole at z equals 0. And recall that I said that pole always corresponds to some atoms which you can add or remove. And that means that when it has a pole at z equals 0, it means that you can start in the very first step when acting on the vacuum. So when acting on nothing, no atoms are taken, you associate this factor. So it has a pole and you can start growing the atom from here. So we call it a starter. And then from there, you can start growing the tower, whole tower of the states. So this is like a highest weight state. But now we can do more complicated stuff. That's what I noticed, what we noticed in a recent paper. So we can try to have two starters. Instead of having just one highest weight state, we can start with the two starters and start growing the crystal. And at some point, they might begin to overlap. And in which case, you might want to eliminate the duplications. And in that case, you want to eliminate that. And that's done by including this factor in the numerator, which is this 0, which eliminates unwanted poles. So this vacuum charge function takes this form, 1, 0, and then 2 poles. Well, we can also do other things. For example, we can have the crystal here, and then another. So starting from this starter at z equals 0, coming to the pole, and then we can try to stop the growth of the crystal by placing a stopper here, which is this 0 at z equals zd. Another point. So, these are some examples, and as you might imagine, having arbitrary starters at arbitrary positions, and also poser and stopper, etc., at general locations. Basically, by doing that, you can construct a rather general shape of the crystal and use that for representation. So the set of all possible representations is actually gigantic. And it turns out that these contain some representations, not for the representation, some counting problems. People haven't discussed representations, but people have discussed the counting problems in association with the Thomson-Thomas invariants. So Thomson-Thomas invariants of BPS state counting, there are various different versions. So for example, you can discuss the wall crossings, and depending, okay, so then the answers do change, and you get the different crystal shapes. In this case, it's a finite, infinite, finite size, and those are the combinatorially or answer-wise, enumerative counting-wise, these are represented by this crystal, finite and infinite, and these are regarded as a special case of special classes of the representation of reconstructed. So, well, as far as I know, all the representations, all the counting problem people considered before fits into our framework. So wall crossing can be represented as a change of the representation. Now, not only we reproduce the known representations, known counting problems, But we also constructed some representations which seems to have no counterpart, at least in the literature, as far as the Calabi 3 BPS or state or Thomas countings are concerned. For example, even for C3, the trivial geometry, we can have a representation where this let things stop first. So we stop the growth of the crystal here. Or in the conifold case, the thing people discussed are either infinite in both directions or finite. But you can also consider the semi-finite representations. And these are well-defined representations. And so it's interesting to see if there is any geometry underlying this. But certainly they arise from quantum mechanics. There is associated moduli space. So in that sense, there is a geometry. But I don't know if this has a counting as an interpretation as a Thomas type invariance in the geometry. Now, I have a little bit of time, so I can comment very briefly on how to derive these things. So I just defined it, and I also top down algebras and representations. But you don't have to guess it, actually, because you can derive them from equivalent localization in supersymmetric quantum mechanics. So, so given the data of Quiver and potential, superpotential, that's the defining data of the Quiver Yangian. And then starting that, you can regard that as the definition of the supersymmetric quantum mechanics. And then there's a well-known story of there is associated vacuum moduli space, and there's a supercharge acting on that, which acts like a durable operator or in the complex setup, or a differential operator, as in the most function story of the Witten. And so there is underlying geometry. And then furthermore, we introduced equivalent parameters at some point. And geometrically, these correspond to some omega deformation, regularizing the geometry. And moreover, we established the torus Calabi 3, so there is secretly a torus action. And when you localize the vacuum moduli space with the torus action, you have a set of fixed points, and that's represented by the crystal. Now, you can derive the effective wave function on this geometry, and that's given by the Euler class. That's a supersymmetric localization which people discussed. And this E and F generators, for example. So for example, E generator, that creates an atom, and that plays the role of the Hecke modifications. So adding an atom means adding the rank of the gauge group of 1 in quantum mechanics language. And so you can, we have a physics argument of how to derive it. And it turns out the result coincides with the Fourier-Mukai transform in this product moduli space, defined as incident locus. That's how mathematicians define this action. So by using this logic, we obtained very concrete expressions for the actions of this algebra arising from BPS states counting. And they look slightly different from the Quiver-Yangian representation I talked about. And that's not surprising because in the representation of the algebra, you can change the basis, for example. So you might get a different looking expression. But you have to check but we can check the commutation relations of the generators. And it turns out that in all the cases we checked in the computer program, they coincide with the Quiver-Yangian, which I defined earlier. But in general, this requires a complicated computations. And so we can do the computers to check it, but in general, I don't have a complete proof. But nevertheless, I should say that there is certainly a remarkable structure in between, behind. For example, this is an example of the fine Yangian of GS3/1 hat, so GS3/1. And then there is a known Seri relations, which you can impose in addition to the relations I talked about. So, this sorry, I forgot to say that this is equal to 0. So that's the Seri relations. And so you can try to check that from the equivalent localizations. And it's not obvious if it's 0, but it turns out that if you do the computation from computer programs, then you get some identity like something like this, where the sum of more than 10 terms is equal to 0. And each of these expressions probably is a little bit too small to see, but it's a function of h bar 1 and h bar 2. It's a very complicated rational function. But it turns out they sum up to 0 somehow. So this is the type of cancellation we see. So the fact that we didn't, so we didn't, I mean, we just computed from by definition of localization, and then you produce the correct equation relations in the Quiver-Yangian. So that's a highly non-trivial check. of the statement that the Quiver Yangians do indeed arise. So I think it's time, so let me summarize. So here in this talk, I introduced a new integrable type structure, which I call the Quiver Yangian. And so these are new algebras, and I construct new representations in terms of the crystal melting. And then there is an underlying geometry of supersymmetric Calabi 3 and the supersymmetric quantum mechanics. And as usual, everything comes from the string theory, and there are a lot to be explored, both in physics and mathematics. Thank you.
Thank you very much. Are there questions? Yes, Alexander.
As far as I know, objects similar to Yangian sometimes act on some modular spaces like Hilbert scheme, like cohomology of or K-theory of the Hilbert scheme of points or Quiver varieties. Do you expect anything like this for your algebra?
But yeah, in a sense, what we did is essentially that. So in our case, we didn't construct directly on the action of the modular cohomologies, the K-theory itself themselves, but rather we constructed action onto the fixed points, torus fixed point on the moduli space. Yeah, so that's the structure. But so essentially, I would expect it's the same thing, and. Although so if you're more geometry oriented, you can try to construct action directly on the moduli space and then try to compare. And indeed, for example, there are a couple of nice papers by Jan Soiberman and collaborators who did that. And they obtained the similar structures, I think, for the case of, from our viewpoint, special case of GLM/M. So in those cases, they work out the actions more mathematically and then worked out action correctly. And then they obtained the almost, yeah, I think very similar, at least the structures. And yes, thank you.
More questions? So do these algebras have coproducts?
Yes, let's see. For the Yangian, yes. Although whenever you talk about the coproduct of affine Yangians, there is a formal coproduct. Like you don't care about the convergence, and also more honest actual ones. And the actual ones are complicated. I think, for example, Wei and Nakajima and others had a paper about it, and that's complicated. I don't claim to understand it. But if you don't care about the convergence, etc., there is a formal coproduct you can define by the usual formula. And the structure becomes a little bit clearer when you go to quantum toroidal and elliptic cases, and that's what we are looking at right now.
Okay. More questions? If not, let's thank the speaker again for this nice talk.